Now we're in the middle of, at the end of last session, talking about the formal definition, not just of the PDA. We did that pretty much with the 6 tuple, but we were starting to talk about formal definition of processing. How does a PDA process? So we're talking about your input string is of this form. So say an input string W, and that will consist of symbols, say M of them, in W1, W2, Wm, where these symbols belong to your augmented, including the epsilon, the empty string, alphabet, the input string alphabet. Okay? And you'll go through, no, we didn't, starting, so here's now fresh. So you'll go through a sequence of states as you process the string, as you read it through symbol by symbol. So you go through a series of states of the machine, starting at R0 and then R1 ... Rn. Okay, and these states, they all belong to the set of states, capital Q, and your strings, there'll be strings like this of strings. So a sequence of symbols from your stack alphabet here. Now notice the star here. So these S's here, they are in fact the contents of the whole stack. Like so, well, S0 would be the empty stack, and that's what you start with. But any of these S's in here, they would be a description of the contents of the stack. In other words, what symbols are stored on the stack. So, well, let's say Si. Well, the first element, well, the first symbol in Si would be what's the symbol on the top of the stack, and then the second symbol of Si would be the second most upper symbol on the stack, and the third symbol in Si would be the third thing in the stack, and so on. So these S's here, they're the contents of the whole stack. They're just they're not just single elements; they're a string of elements. And you look on, like at a given moment, you look at the contents of the stack. Each symbol that's on the stack at each level. So if you put all those symbols and put them together, concatenated them, that would be your S. And your left hand side of your S, that string, that would be that would correspond to the top end of the stack. And the right hand of that string, S, that would correspond to the bottom of the stack. Okay? So these S's, you go through a sequence of your stacks changing, and each of them, they belong to, again, a star. And so in other words, you're talking about a string, not just one symbol, but a string of symbols. Each of these S's is a string of symbols. In other words, physically, it's a list of the contents of the stack. It's a list of all the symbols on the stack, looked on as a string. You like concatenating them in a sense, right? Okay, so these W's are the sequence of R's and S's. The stack contents. They have to satisfy certain, well, 3 conditions. Okay, well, your first state has to be the start state. So that's Q0. Now Q0, if you go back to the formal definition, the 6 tuple, the Q0, that is your start state. Okay, so R0 has to be Q0. And you want your stack to be empty. So this content should be nothing. It should be the empty string. So put S0. The condition is S0 is epsilon, the empty string. Physically, you're putting the machine in the start state Q0, and you're starting out with an empty stack. So S0 is epsilon. Okay, you sort of physically intuitive, fairly obvious. Saying here, this condition, this first condition, 1, 2, 3, specifies that the machine M, it starts out properly. In other words, it starts in the start state and has an empty stack. So it's sort of fairly obvious. Okay, now second one, it's involving the R's and the S's, talking about how the sequence of states changes and how the strings change. We're getting into more detail now. And the fuzziness we had a bit before about how do you manipulate the stack, that will become clearer now, because we're into more detailed description of what's going on. Right. As far as the stack's concerned, no, wait a minute. No, we're talking states. Now remember the transition function, you take an ordered triple, the current state, the next symbol to be read in your input stream, and A is the symbol at the top of the stack. Okay? There are your three parameters. The transition function deals with those and gives you the next move. And the next move, remember, is an ordered pair. The next state, and what you write onto the top of the stack. So it was A, and now you're going to overwrite that A with a B. Doesn't say anything about reading, so still a bit fuzzy. All right. So it looks as though this A is going to get overwritten by this B. All right. Now let's say SI, so at the ith step, the stack contents are AT. Now what does that mean? That means the top element, the top symbol in the stack is A, little a. And T is the rest of the stack, the contents of the rest of the stack. So T will belong to gamma star. And this is the set of strings, all possible strings. Okay, so at the ith step, the contents of the stack, SI, will just be AT, and that A, it's the same as here. A is the top of the stack. And remember, the left-hand side is the top of the stack, and as you move to the right here, you're going lower and lower into the stack. So T is the rest of the stack except for the top position, which has A in it. All right. So you execute your next move given by your delta function. So what will your S at the I+1th step? What will your stack look like now? Well, the A will have been overwritten by B. Okay, so this is your next move. Go to this next state, which is I+1, and overwrite the top of the stack by B. Well, it was A, well now it's B. So now your S of I+1, like next step, the next move, or part of it, will be BT. Remember, T is the rest of the stack. And B now is at the top of the stack. That's the symbol at the top of the stack. Okay. Where A and B, well, they're just members of your stack alphabet. Well, augmented stack alphabet. Right? Now, what's going on here? Well, it's ensuring that this is the next state. Okay. And it's overwriting the old top of the stack by this new one. Okay, using the delta function, the transition function. Now you probably, as I was, can be confused about the use of the stack. Well, how about reading stuff? How do you, if you're just overwriting all the time, how do you like make the stack longer? Stuff like that. Questions like that. Well, that will become clearer. Okay, just wait a bit, right? And third condition is that the last state here, for this string to be accepted, this last state, obviously has to belong to the set of accept states. Now that's old hat, that's not new. Okay, so that's much the same as we've done earlier with finite automata. Alright? Okay, so that's the end of the formal definition. Well, actually, okay, formal definition. It's still not clear on how you manipulate the stack, but that will become clearer as we get into the examples. Okay, so example 2.14 in the text, we're going back to this language again that we've seen a few times already, and now we're going to provide a formal definition for the PDA that recognizes this language. Okay. It's a formal definition, so we'll use our tuple, in this case a 6 tuple, because it's a PDA, and here they are, and now we'll specify what each of these are. Now you may ask why. You're going to have, as homework, think, analyze, because you're given the PDA, you're given its formal specification, but think it through to get familiar with how it works. There's quite a few details in it now. Okay, so I was just thrown at you, but you're asked to. Well, I'm asking you to think about it. Have a look at each element, each part of it, and persuade yourself why it is the way it is and why it works, that it does work. So here's our first full description of a PDA actually working on a concrete language, trying to recognize a concrete language. Okay, so the set of states, well, we have 4 of them, 4 different states. Why 4? Well, that's what you need to do for homework, figure out why that's the case. The alphabet of the input string, binary, just 0 and 1. Yeah. The alphabet of